video. And I decided, why not record this live? It'll be very similar, but it might be fun if you're joining it and seeing it happen. And I am decided to talk about osmotic pressure. And the reason for this is that on a past exam, there were a lot of students who missed a problem on this. And so I thought it might be helpful to talk about something called the colligative properties first. So I got my calligraphy pen ready, but it's not holding the ink, so I'm going to. By the way, a lot of you make comments on my pens, so I'm gonna show you a little bit how these work. There's this part that's a holder that's wooden, and then this is holding what's called the nib. It's called the nib that I then dip into the India ink, and this comes off. So I'm going to remove this because it's not working well. And I'm going to replace it with this one that's gold colored. Alright, so let's put this back in. So as I was saying, I wanted to talk about colligative properties with you, because it is something that goes beyond just osmotic pressure. And it has to do with the concentration of particles in solution. And it's very interesting how the concentration of particles, no matter what the particles are, can affect these properties. Alright, so let's make a header here. Colligative. The origin of this word I do not know. But there's several colligative properties that are useful to know about and affect our everyday life. Alright. And one of them is freezing point depression. And what that means is not depression. We usually use the word with our emotions, but that the freezing point decreases if there are particles in the water, or really the solvent. Usually we are talking about water, but it doesn't have to be. And essentially what this means is, let's say we have a beaker here. It's pure solvent. And then, let's say we've got another beaker that has the same solvent and the same amount of the solvent, but now we have particles in it. So now we have solvent plus solute, the particles that are dissolved in the solvent. And what happens here is that the solvent has hello. The solvent has a freezing point that is inherent to it. And so let's say it has some certain freezing point, which is a temperature. Okay. But now, when we've added a solvent to it, we can think of it that the solute particles are getting in the way of the solvent being able to freeze properly. So the temperature has to go down and get colder and colder, removing heat from the process to enable the solvent to then freeze. And so the freezing point of this resulting solution, is always going to be less than the freezing point of the pure solvent. So I really like this imagining these particles, these solute particles, getting in the way of that solvent freezing. That helps me envision this better. And remember that it's always going to be a lower temperature that the solution needs to go. All right, so that's one colligative property. Another one is boiling point and how that is affected. And what's interesting about this is that the boiling point, instead of going down, or in other words, depression, it is elevated. So we say boiling point elevation. Because here it is the opposite. We have a pure solvent that has a boiling point. And now there are solute particles that are getting in the way of that liquid solvent from escaping out of this liquid phase and becoming gas phase, which is what happens when we boil something. So again, this visualization of the solute particles getting in the way of the solvent escaping, boiling, requires that you have to add more heat, or in other words, raise the temperature in order for that solvent to be able to boil. So the net result is that the boiling point is always going to be higher for a solution when you have a solute present along with the solvent. Okay, and then one last one, and this was going to be my main point here, was to get to talk a little bit about osmotic pressure. So osmotic pressure is a little bit different from these other two. And one of the ways that we can think about it is that if you have a contraption here, this is not an everyday contraption, but it's really nice for talking about this concept of osmotic pressure. So imagine you have a test tube here, but you had a very clever glass blower who was able to make this tube bent and have two open sides to it. So it looks kind of like this. And these two ends are open to the atmosphere. And there's a separator here that is what we call a sure you can see this, semi-permeable membrane. Okay, what does that mean? It means that it allows some things through and some things are not able to pass through. And in the case of this example of osmosis or osmotic pressure, it allows solvent to pass through, but it does not allow any particles or solute particles to pass through. So let's make note of that. That it allows passage of solvent. Okay. We're going to talk about an example with water being the solvent. So imagine we pour in some water. So we have water that's filling up this contraption. But on one side, it's water that has particles in it. So let's say it's salt water, for example. So we have salty water on this side. But on this side, it's pure deionized water or distilled water. There's water and nothing else in it over here. So what nature does is that spontaneously, if we think about our thermodynamics and things that happen without input of energy, is that we will see that if you want to think of what nature does in a descriptive way, we can see that nature does not like gradients, and it tries to equalize things, reach an equilibrium. And so what will then naturally happen is that the water that's on this side will spontaneously flow towards the side that has a higher concentration. And the idea here is that it is diluting this side. Again, this happens in a way to make the concentrations more equal to each other. Where this concentration is clearly very low, it's pretty much zero. And this concentration is definitely higher. We have that salt present. So, since this membrane allows the solvent, or in this case, the water, to pass through, it will naturally, spontaneously flow this way. And ultimately, because of that, the level on this side will go down. So it will reach some lower level. The level on this side will go up. Equal and opposite. Alright, so then you say, alright, cool picture. What does it mean? Osmotic pressure is the pressure required to stop this from happening. So in other words, pushing down on this side, how would you stop this from naturally happening? That's how we define osmotic pressure. So, therefore, osmotic pressure is greater when you have a higher concentration of particles in solution. And we can calculate what osmotic pressure is. I'll give you the equation here. The symbol for osmotic pressure, as opposed to gas pressure, we symbolize it with capital P. Osmotic pressure, we use a different symbol. It's still capital P, but it's the Greek symbol or Greek letter pi. So it's a capital pi. So the osmotic pressure is equal to what we call the Van't Hoff Factor. I'll tell you what that is in a moment. Times the concentration of the particles in solution. All right. Remember, osmotic pressure will go up if it's a higher concentration. So makes sense that these are directly related, directly proportional to each other. This is multiplied by the gas constant R and the temperature in Kelvin. So this is temperature dependent. Okay. So here's our osmotic pressure. This is in units of atmosphere. The Van't Hoff Factor is unitless. Again, I'll tell you what that is. Promise. Molarity. Moles per liter. Okay, the gas constant. Alright, so gas constant. We are going to use the form that's used for gases where we have liters, atmospheres per mole Kelvin, as opposed to the gas constant that is joules per mole Kelvin. Okay, because we want to be able to get liters in there, right? So the form of the gas constant we want is this one, 6 liters, atmospheres per mole Kelvin. Okay, so let me separate these out. So gas constant, and then our temperature that's in Kelvin. So here, just wanted to show you all the units and how they work out. So moles, cancel with moles, Kelvin, cancel with Kelvin, liters, cancels with liters, and that leaves behind atmospheres. Okay. So the calculations for these kinds of problems with the osmotic pressure, they're not too bad, but I want to point out the Van't Hoff Factor here. So let me move this up and talk about what this is. And that is, let me write this out, Van't Hoff So this is where it's very helpful to remember about your electrolytes and about the solubility of ionic compounds and things like that, because that is going to affect what that value is. So let me give you an example. For sodium chloride, okay, this is a single formula unit, but in water, it breaks apart. So if we were to dissolve this, I'll just say put water over the arrow here, we get aqueous sodium ions and aqueous chloride ions. And what that means in terms of particles in solution is for every 1 mole of this unit that we have here, we have 2 moles of particles in solution. So, what that means is that the Van't Hoff Factor for sodium chloride is 2. Because osmotic pressure depends on the total number of particles. So if you have a 1 molar solution of sodium chloride, that's just referring to the single unit, formula unit of sodium chloride. But effectively, you end up with 2 particles in solution. So in the case of osmotic pressure, you need to take that into account, and that's why you need to invoke the Van't Hoff Factor and put a 2 right there. Okay. Well, I hope that clarifies why you need to have a 2 in there, and also gives you some idea of why the number of particles in solution affects osmotic pressure, why it affects boiling point elevation, as well as the freezing point depression. So, thank you. Thank you so much for joining me. It's really cool to have, I have Orion here with us and Christina, and it's pretty fun to do this live. I've never done it live before, so very much enjoying it. So I hope you're having a good day or a good evening wherever you are, and let me know what other questions that you might have, and I will create a video for you. I'm working on a couple of them currently, an organic chemistry one, and I'll get some other general chemistry ones going too. Alright, thank you so much, and I will see you again very soon.